For today's lesson, we're going to be talking about how the energy changes during a chemical reaction. So we draw diagrams called potential energy diagrams to show how the energy changes from turning our reactants into products. We can gain a bunch of information from these diagrams. So one variable described on our diagram is called the heat of a reaction. So the symbol for our heat of reaction is a delta H. So it stands for the change in heat of a reaction. So during a chemical reaction, energy is needed to break chemical bonds in our reactant side. And then energy is given out when bonds are made to form our products. So the difference between the energy needed to break the bond in the reactants and the energy given out when new bonds are formed is what we called the heat of the reaction, or delta H, the change in heat. Remember last time in class we talked about what delta stands for. So our change in heat for our reaction. So let's take a closer look at what happens in this reaction. So methane and oxygen making carbon dioxide and water. So here we have our methane molecule and our oxygen molecule. So in order for energy or for our reaction to take place, we have to break these bonds between the carbon and the hydrogen and both of these bonds in our oxygen. So it requires some energy to do that. So usually we have to heat them up. So like in lab when we're using the Bunsen burners, which is methane gas, or which is a gas somewhat like methane, we have to add a spark or use the lighter to get it to start to react. So energy is absorbed to break those bonds. So our bonds are broken, our molecules rearrange. Now to form our new bonds to make our water and our carbon dioxide, we'll actually give off some energy in doing that. So energy is released when new bonds are formed. So most of these molecules will be more stable and more happy when they form bonds. So energy is released during that process. Okay, so we have two types of reactions. So here in an exothermic reaction, energy is given out. So that means our reactants are higher in energy than our products. And the difference between them, which would be a negative value, would mean it's an exothermic reaction. So heat is given off in the reaction. So more energy is given off than is taken in when we form those bonds. So our products are at our lower energy and our reactants at our higher energy. We have a delta H value that is negative. The opposite happens in an endothermic reaction. So here, more energy is needed to break those bonds than it gives off when it reforms them. So this is an endothermic reaction. Here our delta H would be a positive value, so like positive 5,000 kilojoules. Our products are going to be higher in energy than our reactants. So energy is on the y-axis here. So reactants are lower, products are higher. So we have to add a lot more energy to get this reaction to work. So more energy is needed to break the bonds than is given off when they reform. The opposite was true on this one. So more energy is given off when they reform than what was needed to break those bonds in an exothermic reaction. So negative delta H for exothermic, heat exits. Endothermic, like enter, heat is taken in, which has a positive delta H. So here kind of summarizes this. So energy is given out to the surrounding area, so it should feel warmer to you. Endothermic reactions, energy is taken in, so it would feel cooler to you because heat is moving from your hand to the reaction. Delta H is negative for exothermic, heat exits. Delta H is positive for endothermic. The products have less energy in an exothermic, products have more energy in an endothermic reaction. So we saw somewhat of a part of this diagram on our last couple slides, but potential energy diagrams show how the energy changes from reactants to products over the course of a reaction. So we're going to talk about the information we can get from this graph. the different areas on our graph that we can describe, where our products are, where our reactants are. What does this hill mean on this curve? Is this an exothermic, endothermic reaction? So they show how energy changes during a reaction. So for an exothermic reaction, this is what the graph would tend to look like. So your reactants are going to be here on the left side, just like they're on the left of an equation. And the reactants are going to be higher in energy, and our products are going to be in lower energy. So it always starts high and ends up going lower for an exothermic reaction. So you always see this kind of trend. So reactants are here, your products are down over here. The top of this hill is called an activated complex. So when our molecules collide, they actually form this intermediate molecule, and we call it the activated complex. It's temporary, it does not last very long, and is very unstable. So it's the arrangement of atoms that form as the products break, but before we can, or as the reactants break, but before the products can reform. So the activated complex is at the top of this peak on our curve. Now our activation energy we talked about last time was the energy required to get a reaction to work. And so we can measure that value between, if we find the difference between our activated complex and our reactants. So let's say we have a scale on here. So let's say this is at maybe 200. Our reactants are at 150. So if we wanted to figure out how much energy is required to go from our reactants to our activated complex, our activation energy, all we would do is subtract the difference. So we would take our 200, which is our activated complex, minus our reactants, 150, and we would get 50 for our answer. Usually kilojoules is the unit for energy. So the difference between our activated complex and our reactants is our activation energy. Now we can also get how much our heat of our reaction is. So the heat of reaction is the difference between our products and our reactants. So let's say again we're at 150 for our reactants. Let's say we're at 50 for our products. So we just find the difference between them. So we would take our products where we end up, remember it's always final minus initial, minus our reactants, which is 50, and we get a difference of negative 100. Remember, it should be negative because negative means exothermic. So an exothermic reaction. What would this reaction look like if it was endothermic? So for endothermic, it's kind of the opposite. So we start low with our reactants and our products end up being higher. So we see this general trend occurring in an endothermic reaction. Again, our reactants are going to be here on the left. We could read how much their energy is at if we had a scale. Same with our products. Our products will be over here at the end. We have our activated complex still at the top of the hill. If we subtract the two, our activated complex and our reactants, we can get our activation energy required to start our reaction. And again, the difference between our products and our reactants will be our delta H, and this time it will be positive. So let's give this a scale. So let's say we're at 100 here. Let's say this is at 150 at the top of our hill, and let's say this is at 50 again. So if we wanted to calculate our activation energy from our reactants to our products, we're just going to do a little subtraction. So we would take 50 minus 100. We would get our activation energy of 50. Now let's do the other one. So our delta H, we're just going to subtract the two. So we would take 100 minus 50, and we get our delta H, our heat of reaction, of 50. Now it's positive this time because it's exothermic. On this next slide, it kind of summarizes what we were talking about, how we're calculating our delta H and our activation energy. So again, the delta H, the heat of our reaction, is always products minus reactants energy. activation energy, we're always going to take our activated complex minus the energy of our reactants. So if we're looking at this graph here, A would tell us the energy of our reactants. So I'm going to put an R there. C would tell us our energy of our activated complex. D would tell us our energy of our products. B would give us our activation energy, so our difference between our activated complex and our reactants. And let's give this one an E. So E would give us our delta H, if that was labeled on our graph here. So let's try this example problem. So the potential energy diagram represents a reaction that is endo or exothermic. Take a guess. So our general trend here is an exothermic reaction. So our delta H has a value of, right here, -10. Difference between our reactants, which are over here, our products over here, activated complex at the top, and our activation energy would be 15. Let's try this one. So let's say we go in reverse. So when we have a problem that says go in reverse, we just swap where our products and reactants are. So if we're going in reverse, this would become our reactants, and we're going to go up the hill first and then down. So we're going to go the opposite direction. Means our products are over here now. Activated complex still at the top. Okay, so if we go in reverse, then the trend would make it endothermic. Our delta H, difference between our reactants and products, instead of being negative, because we're going up in energy, should be +10 now. And our activation energy would be 10 plus 15 to get to the top of that hill now. So it would be 25 kilojoules. So if it's exothermic forward, in reverse, it's always going to be the opposite. Let's try another example. So here we have a potential energy diagram. It represents, take a moment to look there. What trend does that match? So it should be an endothermic reaction. So reactants down below, products are higher, making it endothermic, activated complex at the top. So our delta H would be I think that's pointing at +5 looks like there. And our activation energy would be our 20 kilojoules. Let's try another one that's reverse. So here we have a reverse reaction. So remember, when we're going in reverse, we start with our reactants down below, products over here, activated complex at the top still. So if we're going in reverse, it would make it an endothermic reaction. Our delta H, the difference between reactants and products. Remember, instead of negative, because we're going up, it becomes +15. And our activation energy, we're just going to add those two together. So 15 plus 25 to get to the top of the hill. And we get a value of 40 then for our activation energy. So you're going to be doing a bunch of these on the homework today. Just remember that forward, we have our reactants, products down below. General trend here. The difference between our reactants and the top of the hill, that's always our activation energy. The difference between our reactants and products, that's always going to be your delta H. And then a general trend like this one is showing would always be exothermic. But if we're going in reverse, then it would become endothermic. And we're going in reverse, we just flip-flop our reactants and our products. Activation energy is still at the top. This time our activation energy would be this entire side. Our delta H stays the same, just flips the sign. Difference between reactants and products gives us our delta H. So by looking at some of these curves, how do we determine how fast a reaction is going to occur? And so to determine that, we look at how much our activation energy is. So the lower the activation energy, the faster the reaction is going to occur, regardless whether it's endothermic or exothermic. So if we're looking at these three curves or graphs, we have activation energy for our first one here of 15. Our second one has an activation energy of 25, and the third one has an activation energy of 20. So this one's going to be the fastest, number one. This one would be the next fastest, and this one would be the slowest in third place. So it all has to do with how big that activation energy is, how much energy you have to put in to get the reaction to work. So the less energy you need to put in, the faster the reaction is going to occur.